Okay, folks, this is the final part of flight mechanics. We've dealt with all our equations we've got here. In this part of the textbook, page 170, they're relating the lift to drag ratio to the angle. Okay, so we need to be able to play around with these equations so we can manipulate them to solve problems. Okay, so lift to drag ratio. What is it? Okay, it's just basically a measure of how efficient or efficiently an aircraft glides. Okay, so it's found by taking your lift force and dividing by your drag force, okay? And that's why it's a ratio, because we divide one by the other. Now, if the lift is really high and the drag is really small, we get bigger number over a smaller number, we get a bigger number overall. As the drag gets bigger, lift to drag ratio starts to get smaller and smaller. Okay, so we have 100 on top and 1 on the bottom. We'd have a lift to drag ratio of 100. If we double the drag and make it 2 and leave the lift at 100, we get 50. You can see the numbers are getting smaller. The aircraft will be gliding less efficiently. Okay, so if you want to pause and just write down what lift to drag ratio is, that might be helpful. Copy that down. And now we're going to talk about how it's related to the angle of ascent or descent. Okay, so talking about gliding, we can just get rid of the notion of thrust, okay, because we're talking about a gliding situation. And we're going to relate it to this angle, okay, theta. Okay, so if we get rid of our thrust, get rid of it, we end up with tan theta is equal to minus d on L. So we're already close to a lift to drag, but we've got the reciprocal, we've got drag over lift, okay? Now, a little reminder, I know a lot of you guys are extension maths, but a few of you might not be. To find the reciprocal of something, when you just flip it, and that's the same as saying 1 divided by. Okay, if you don't believe me, if we say we've got the number 2, actually let's make it the number a half. Okay, we've got a half, and we find the reciprocal of it, it's equal to 2 over 1. Okay, because we've just flipped it. Okay, and that's equal to 2 because anything divided by 1 is equal to 2. Okay, so that's the same as saying it's the same as saying 1 divided by. So if I took this and I wanted to find the reciprocal of a half, I could say 1 divided by a half, which is the same as saying 1 times 2 over 1, because that's how you do your fractions. I hope you know to do that. And so we end up with 2. So 1 divided by is how you find a reciprocal, which is why in your Copeland text, they say that lift to drag is equal to 1 over tan theta, okay? Because they've flipped this and therefore they've had to divide this by 1. That's why we divide by 1. So lift to drag ratio is equal to 1 over tan theta. So now we have an equation that relates our lift to drag ratio to our angle of ascent or descent. Looking over here for a minute, just as a little bit of a reminder, we have our equation tan theta equals T minus D over L, thrust minus drag over lift, okay? If you remember that equation, okay, you're in good stead to remember nearly everything, because to get to this equation, you just have to say, get rid of thrust, find the reciprocal, okay? If you remember this equation, you will also need to remember just in your mind that for a small angle, okay, we can get rid of tan, and the L can become L or a W, because L is approximately equal, lift is approximately equal to the weight force in situations where theta is very small. And therefore you get these two more equations where we got rid of tan and we can either have a W on the bottom or an L. Because like I said, for here, the small angles, W is approximately equal to L, okay? So that's a wonderful way of remembering the equation, okay? scaffolding and the memory of it. I'm hoping that helps a bit. Nothing's going to suffice as much as studying really, really hard. Okay, so let's look at the example they've given on page 170, which is example 3.3. Now, they've done a free body diagram, and that's a fine way of answering the question, and we will look at that answer. But we'll also look at remembering our flight mechanics and our forces and analyse it. Okay, so we're given some information here. A glider plus a pilot has a mass of 850 kilograms. So we've got a mass. Let's circle that, okay? It's descending at 15 degrees, so we've got an angle, at a constant velocity. As soon as you see that constant velocity situation, you're dealing with a system of equilibrium, okay? Remember constant speed ascent, when we looked at that, all the forces are balancing, okay? So they're saying calculate the lift, and then calculate the lift to drag ratio, okay? So if you were to draw your flight path, okay, and we know that we've got a 15-degree angle, that's the ground, okay, it's 15 degrees. We've got an aircraft. I might draw the aircraft in another colour just to make things interesting. So we did an ascending aircraft. We didn't do a descending aircraft, but we're going to be dealing with the same situation. Okay, we know that we have a weight force acting straight down. Okay, we know that we can break that up into components acting this way and this way. And we do that because our lift force is always going to be perpendicular to that flight path. Okay, so that is our lift. Okay, so now we need to say to ourselves, well, our lift is going to have to be, because we know that the sum of forces perpendicular to the path is going to be equal to 0, and the sum of forces in line or parallel with the path is going to be equal to 0. We did that when we did our ascending aircraft, okay? So we know that this component of the weight going this way is equal to W cos theta. And we know that this force going this way is W sine theta, okay? And we know that the whole system is in equilibrium, so this force here, W sine theta, must be balanced by a force going in this direction, and we know what that force is, it's drag. Okay, so I'm not answering this question the same way as Copeland does, but I'll get to the same answer. Okay, so we can say to ourselves, we know our weight is equal to 850 kgs times 10 meters per second squared, because we use 10 meters per second squared for engineering, and we end up with 8,500 newtons, or we do for this course anyway. 8,500 newtons, okay, so our weight force is 8,500 newtons. So we know that our lift force has to be opposed by an equal and opposite force, which is this component of our weight force, okay? So lift is equal to weight times cos 15 degrees. So lift is equal to 8,500, that was our weight force, times cos 15 degrees, okay? Now drag has to be equal and opposite to this one, okay? So drag is equal to, so let's work out a lift first. I said first thing they wanted us to do was work out lift, okay? So, oh, there it is there. 8,500 times cos 15 degrees. So we get out our trusty calculator and we say 8,500 times cos 15, and we end up with 8,210.4 newtons. You could turn that into kilonewtons if you wanted, but that's your answer, okay? Then we need to work out, then they said, and then calculate the lift drag ratio, okay? Now, you could just say, now that I know my lift, and I know my formula for, we remember we talked about lift to drag is equal to 1 over tan theta. Okay, we know that we know our theta. Okay, so we can use this to say lift to drag is equal to 1 over tan theta. So if I was to try and solve this problem by saying, 1 over tan theta, let's try it, 1 divided by 10, 3.73. Okay, so lift to drag equals 3.73. Okay, so that would get us to a solution of our lift force and our lift to drag ratio using theta. Okay. Also, just to prove that my vector diagram is correct, okay, we said that lift is equal to W cos 15. We also know that drag is going to be, our drag is going to be equal and opposite to W sine 15. Okay, so we could say drag is equal to weight, which is 8,500, times sine 15. Okay, and then if I was to take that and divide by that, I should get 3.73. So let's try it. 8,500 times cos 15 equals, divided by drag, 8,500, I've forgotten my brackets, 500 times cos 15 divided by bracket 8,500 times sine 15, close bracket, equals 3.73. Okay, so L to D is equal to 3.73. So that's two ways you can do it. You can use your actual calculations, lift to drag, and the vectors that you can see here, or like they wanted you to do, that 1 over, lift to drag is equal to 1 over tan theta gets you there really quickly, okay? So that's, if you understand the forces acting on the aircraft, okay, and remember for these ascending or descending that you're dealing with, lift is perpendicular to the wing, so you're dealing with a force that's perpendicular to the actual direction of ascent or descent, okay? You'll be able to nut it out that way, okay, work it out that way. But what they've also done, and I'll show you the way they've done it in the Copeland text, is they basically turned around and said that this whole situation is in equilibrium, and you know that if you have three forces, lift, drag, and weight, because we don't have thrust in this situation. Now, Copeland did it a little bit different. In the Copeland text, he's basically said that we know that we're dealing with an equilibrium situation, so all the forces have to equal. When you add them as vectors, you have to end up with a resultant of 0. So if you have weight and you have lift and you have drag, three forces, they're going to make a triangle. The triangle will be closed, okay? So you need to remember that. So he's done a free body diagram where basically he's drawn the weight vector going straight down. You know, it's equal to 8,500. We know that our drag, if the aircraft is descending in this direction, is going to be going up at 15 degrees. And we know our lift is perpendicular, okay, to our drag. And he's then done a triangle where he's gone weight, drag, and lift. and he's gone, that's 15 degrees, lift to drag, it's going to be 90, and that's going to therefore be 75, and he's used trigonometry to say, to work out what his lift is, okay? So he knows his weight value is 8,500, and he's used that by saying opposite on hypotenuse, so sine of 75 degrees is equal to L over 8,500, therefore L is equal to 8,500 times sine 75 degrees. Eight, 2, 10, yes. So that's the way he's done it. Now, if you're a bit like me, you'll be saying, well, how did he work out these angles, okay? And there's a little bit of geometry involved in that. So if you don't do it via the method that I just showed you, balancing forces acting along, perpendicular and along, okay? You've got to work out those angles in that free body diagram, okay? So the way to do that, you need to add your arrows tip to tail. So you can take this drag vector and you can move it down here so that it's going up in this direction, okay? And then you can take this lift vector, okay, and close the triangle, okay? So you end up with a closed triangle, which you then might be saying to yourself, we know that that's 90 because lift and drag are at 90 degrees to each other, but how did he work out that angle and that angle, okay? It's probably, you can probably think of an easier way than this. I'm probably making this harder than it needs to be, okay? But we know that that's weight, that's drag, and that's lift, okay? So we know that because this is lift and drag, we've got 90 degrees here, we've got 15 degrees here, so 15 plus 90, in a straight line, we've got 180 degrees, so that means we've got 75 degrees there, okay? By doing that, we then know that we've got, because these are vertically opposite, okay, that becomes 75 degrees. And then we know because this is a right angle, because it's going straight down, this becomes 15 degrees. So you have to do a little bit of mental gymnastics to get to that point. And then you've got 15 plus 90, 180 degrees in a triangle, because 180 degrees, you end up with 75 degrees down here. Okay, so you can use that method, free body diagram, closed triangle. That's another way of doing it. Okay, so I've shown you two ways of doing it, but I think the way of relating it to that diagram that we studied for an ascending aircraft, where you know how to break down the vectors into components that are parallel or perpendicular with the path, that's probably the best way of solving the problem. Have a go at thinking about both solutions, and we'll see you in the next video, next segment of the course. See ya.